My
just weren't
pointer
clicked
has to be on.
Yeah, you were clicked
Okay,
into the other.
you're starting.
Long time lapse. How was it? Now put down the put on 2019.
Whatever.
It's from yes, look at that. Sorry for the delay. This is Tone One by Suchit and Akhil. And this is the meeting flag. SIGPwny BC.
Just eight A's, eight B's, and eight C's.
So, what is home? A more descriptive term would be binary exploitation. So, the exploit abuses mechanisms behind how code is compiled and executed with certain functions in the C library or in compilation. You can exploit vulnerabilities to give extra input to certain functions and overwrite certain values on the stack and elsewhere. So it deals with what the CPU actually sees and executes near the hardware level. And then most modern weaponized valuable exploits fall under this category. So this is real stuff. We have seen it in the wild and it continues to be a problem in systems today. Now, this is hard stuff, so I want you guys to ask for help. If you are stuck on something, look it up, ask your peers, ask one of us. It is really imperative that you understand exactly how an exploit and attack chain works because these challenges flow one into the other. So understanding exactly how, pwn one works will help with pwn two, pwn three, etc. And you should feel free to ask your nicks, of course. So programs are just a bunch of numbers ranging from 0 to 255 bytes. And then each number is stored in an address on your computer. And the ranges are from 0x0 in hex to 0x. You can understand this is basically a massive list or array of stored values on your laptop. And then bytes the program serve one or two of key purposes is either an instruction, so telling the processor what to do at a specific junction. Let's say it was to be print something or to jump an instruction to go to a specific function, etc. You get the gist. Or there's also data that's stored, which has some special meaning used by instructions. You can use your basic variables to more complex data structures and classes. So for a larger number, a letter, or a memory address in the case of coders. And this is the main memory layout of your laptop. So you have your instructions at your lower addresses. You have initialized globals, uninitialized globals, and then the heap, which goes up, and the stack, which goes down. So at your highest addresses, OX, yada, 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 that is where your runtime data is usually stored.
This is just a personal rant, but you'll see due to security issues, BSS will almost always be initialized as zeros. So modern compilers tend to put zero initialized variables instead of BSS, instead of data as having to be zero. So it's not necessarily uninitialized. You can just think of it as initialized as zero, or maybe it doesn't have a default value, but it's zero.
Thank you for that. So we care about the instructions and the stack for all intents and purposes of one, as we'll see as we go on.
All right. Now we'll talk a little bit about the stack. I think we won't go through we won't spend too much time on this because I think for the assembly meeting we went over this. So if you don't understand some of this stuff, go back to the assembly meeting and also review these slides because they have a lot of content beyond what I'll say in these presentations. So Okay, so now we're going to talk about specifically in the context of calling a function, what does the stack look like? Specifically, how do we allocate a stack frame and what happens to things on the stack as the function progresses? So first, like before we call this function the stack, there would be prior data on the stack, and the stack grows, remember, from high to low addresses. And we'll have some stack pointer that points to the top of the stack. And then when we call a function, what happens is we need to figure out where to go after we have called the function. So we put something called a return address on the stack. We'll talk about that a little bit more later. But and then after that, we put save base pointer on the stack. This is also just another thing that it like a base pointer points to the bottom of the stack frame. It's not as important regarding point two, so don't worry if you don't fully understand what's going on with this base pointer. But then after that, we'll move our base pointer to the current top of the stack, and then we'll begin allocating things like local variables, like etc. Anything that's allocated on the stack within the lifetime or within the execution of this function. And after that, what happens is at the end, towards the end of the function, we have this epilogue where we will move this base pointer essentially back to what it was before, which is what the save base pointer was. And then we'll move the instruction pointer to what the return address was. So we can go back to whatever we were doing, whatever comes directly after the function call in the and so yeah, so in summary, like we have some registers for our function arguments, and then for the function call, we allocate a return address, or we push a return address to the stack, a base pointer to the stack, and then we put whatever local variables to the stack. And this is important for the actual exploits that happen in PWN I, which you'll call smashing the stack. So let's say we have a function like this, this vulnerable function. It allocates, I guess, 2 arrays of 8 bytes or 8 characters onto the stack, and then it gets input from the user to put values into this the second array, the one that's at the top of the stack, and then it prints the value of the first array, like whatever's in the first array. Does anyone see what might be an issue or what might go like what might be unintended, something that could happen here? Does anyone have any ideas? Yeah.
You write something more than 8 characters.
Yeah. So this gets function doesn't actually check whether we like how many bytes we write. We can write way more than the buffer that we're actually reading into. So this is the function that's sort of centered around all of our challenges for PWN I. So yeah, so this function is very dangerous. You should never use it if you're writing C. But essentially we'll read any amount of bytes from the user and just write it to a buffer or an address. And so because of that, we can overwrite things in memory that wasn't necessarily intended. So here, if we write 8 A's and 8 B's, then the puts call will actually the puts call at the end of the vulnerable function, which just prints the value of the buffer to the to output, will print this BBBBB thing because we overwrote it with our input. So yeah, as you can see, the first A's will go to the stack bar 2, and then the 8 B's will go to stack bar 1, which is what ends up being. So now this seems like kind of like doesn't seem that, I guess, dangerous in the sense that we just changed something being printed, but we didn't actually like, I guess, break anything. But this is where the return address becomes important. So because the return address is also on the stack, we can overwrite this value to essentially jump to wherever we want at the end of a function. So yeah, again, what a return address does is it just is essentially stores where you should go after the function is done executing. So if we can change that, we can go wherever we want. So here, for instance, let's say we have like a win function. It's at this address 80442232, and we want to, let's say we want to call that function, but that function isn't called anywhere in the program. It's just there. So here what we can do is we can overwrite this return address on the stack using this vulnerability that gets however many bytes you input and doesn't check any bounds. So we can overwrite this return address to point to the swing function. So it would look something like this exploit, the 8As would go to the stack bar 1, and then 8Bs will go directly after that, which is the save base pointer in this case. And then this address that we wrote in little endian bytes, which you can't actually type directly into your terminal, but you could send it using phone tools or echo or something. This will actually overwrite the return address so that the function jumps and calls win right after executing vulnerable instead of going back to main or wherever it's called from. So also one other thing that I want to talk about is some things that sometimes come up in code challenges are integer overflows. So for example, you can get something like an out of bounds read in an array or something by decrementing an integer maybe so low that it wraps around to the highest value of an integer. Essentially, a lot of times this can be useful for getting buffer overflows or just out of bounds reads, things like that, out of bounds writes. And so yeah, this might come up sometimes. Yeah.
So now we will talk about delivering your exploit. So little endianness, a quick note, basically numbers are little endian in x86, 64-bit, meaning that the least significant bit is stored first at the lowest memory address. Basically, if you had a number like this, you would reverse the way that it's actually stored. So usually you go from, in your general logic, you would store the most significant digit, like the highest value digits first. But with little endian, you would reverse the order, as you can see here, and you go from low to high.
Just to be clear, though, it's the bytes that are in opposite order. So not necessarily all the digits, but the least significant byte comes first. So in this case, with this number, the least significant byte is the 88 portion because each byte is 2 hexadecimal digits. And so that one will be stored first in memory, i.e. at the lowest address.
Yeah, good clarification. It is the byte, not just every single digit by that. So getting function addresses, you can use object dump. And what this will do is you can give the flag of the specific challenge that you want to look at, and then you can pipe that and grep main. So what this is basically doing is it's looking through your challenge file, and it's looking for the function header main. And what this will do now is it'll send you the memory address of where your main function is located. And that could be like your starting point of where you jump into your code initially or where you start reading from. It's also good to have as like a general pointer address to see, what specific address you have to overflow when you're jumping to a function. So you can also do this with GDB, do gdb./child, I for info, and then you go look at the address main, and it'll print out where that main address, where that main function is again stored. And Ghidra, you can just do this by inspection. So if you put the executable file in Ghidra and then you inspect it, it should give you a folder of all the functions, and from there you can find main, and it'll have the address on the left side. So echo is your input, and basically this, if you do the -e, it enables escape characters, which is good for when you want to put in specific bytes, like hex bytes, directly into your echo output. So with that, as you can see in this example, you can echo directly x01/x02, and this will escape the character, so you can actually put that input directly and then pipe it to chal. So this is just useful if you don't want to have to do some wonky stuff with formatting or conversion. You can just put the hex address directly into your challenge. own tools. This is an extremely useful tool because it gives you the ability to like easily and like in a reproducible way connect to challenges and send whatever your exploit is and deliver it every single time reliably. And it's very easy to, I guess, set up, and we'll see it in this example. So for Pwn, you import all, and then what happens is you can just connect remotely. So you just put the website name as well as the port number that you want to connect to. Then you can read the first line. So you do the connection dot receive line. And what this will do is it'll take whatever the website challenge outputs to you, and then it'll print it for you. And then you can just send line. And this format is basically saying that send 8 A's to your challenge. So this will probably overwrite some stack values that you have in like a get function that the challenge has, and you will just be able to do with send line, just send these 8 A's. Then you can do connection on interactive, and it lets you take over. Let's say you've overridden it, and you go to your win function or something like that. It'll let you display that basically. To install, you do Python 3, or is it on Python or just you need Python 3?
Yeah, you should probably be using Python 3. But also, I think there's instructions on the website too. So for installation, there might be some prerequisites other than this hit install command that you might need to do. So just search up install modules or something. It should be the first thing. But also, I can help with that if you have any trouble.
But yeah, this is the command. Pretty simple. Type it in and install modules. So from here, you can also use phone tools. You can send like to a remote connection that you defined earlier. You can set whatever your win address is, and then you can basically chain together like an exploit with the win address. So you're creating an exploit with 8 bytes of A, and then what you're doing is you're adding your win address to the end of that. So it'll overwrite the stack values, and then it'll allow you to get to your return address and overwrite it with whatever your win function is. Basically the example that was shown earlier, but this is basically done in a more automated fashion. Then you can just do connect, send line exploit, and then pop your interactor.
I can just yeah. This is just a little thing also that might be useful. It might not. It probably isn't necessary for the PWN I challenges, so you don't need to worry about this necessarily. But this might be useful for maybe more complex PWN challenges when you want to debug your exploit and not just the program itself. So in this case, you can actually attach GDB to the connection that you create with modules, and then you can essentially run GDB side by side with your exploit and sort of inspect how your exploit is changing memory or basically whatever it's doing with the program.
So the control sheet, as I said, receive line, so you receive input from whatever the challenge page gives you and print it out so you can see which part of the program you're on. Send line, it's how you send your input to complete the challenge or to overflow stuff. Then this would just be how to format your addresses in either 64-bit for either 64-bit or 32-bit addresses. And then if you run elf and then whatever your file is, it allows you to load addresses directly. So you can look at like symbols such as, in main and stuff like that and look for it, and then load these things locally and display them for yourself.
Yeah, one more thing is, for the P64 function is very useful, especially if this little endian stuff that we talked about earlier is a little bit confusing for you. This P64 thing converts an address to little endian bytes for you to send over your connection. So yeah, this is something you're probably a lot. Very important. Yeah, I can talk. So as we talked about, there's an integer overflow challenge. Or that might be useful. There's also these bug bounty challenges 1 through 6. They each kind of build upon each other. So and for most of these, or I think for 1 through 4, they don't. They print a sort of visualization of the stack for for you to see what your exploit is doing. So you probably don't need GDB for those, or you probably don't even need to run the program locally. And then yeah, 5 and 6 require some concepts that we did not talk about in this presentation. We'll talk about in Pwn 2. So if you're feeling, I don't know, if you finish these first 4 really fast and you're like up for another challenge, try them out. But otherwise, we'll talk a little bit about how you go about solving these in the next Pwn meeting. And then we also have Pwny Mark, which is another challenge about like yeah, Pwn primitives.
So next meetings would be this Thursday. We'll be presenting Crypto 1, and this is just the basics of cryptography, including ciphers, symmetric encryption, and more. So stay tuned for that. There are a bunch of crypto challenges in CTFs, and we need good crypto people. Next Sunday, we'll be doing Pwn 2, which will be an extension of this. You'll learn about more advanced binary exploitation techniques and build on what you learned today in Pwn 1. This is the flag again, and obviously meeting Caltech can be found at SIGPwny/meetings, SIGPwny.com/meetings. Cool, thank you.
Also, I just want to ask, who here has an M1 Mac or Apple Silicon Mac of any kind? Yeah, so because your like the architecture on your computers is different, you probably will not be able to run the binaries that we give you locally. And like the exploits won't work the same locally either. So for the first 4 clone challenges at least, or the bug bounty challenges at least, it probably doesn't matter because you should be able to solve them like just on the remote. Like you probably won't need to run them locally. But when you do need to run things locally, there's a few options. You can I think SIGPwny has a like a repository called Pwn Docker, which you can use to spin up a Docker container to run programs. Also, you can, if you have access to a Linux machine somehow, like maybe over SSH, you can just do your exploit development in there. That's what I do personally, because I also have a M1 Mac. And yeah, other than that, yeah, if you have any if you're running it to any problems with M1 Max stuff or just actually anything at all, feel free, don't hesitate to ask. Yeah, we'll be happy to help. Yeah, thanks everyone.